Welcome back, students. So as we mentioned in the previous video lecture, that in this particular lecture, we will be looking at the equipment itself, the equipment that is used for tensile testing, which is UTM, uniaxial tensile testing machine. So let's start with what are the important components of a testing machine. So let me draw a simple schematic of how a UTM looks like. So there is a frame. It is supposed to be vertical, although my drawing may not show it exactly like that. So this is a frame, and this is called a double frame, double vertical frame. There can also be a single vertical rod for supporting it, and it all basically determines what will be the total cost of the equipment. And in here, you would have a testing jaw somewhere over here. This is the bottom jaw, this is the top jaw. And this top jaw would be connected to a moving part, which will be called a crosshead. So this part that we are looking at, this is the frame. This is one important component. Actually it should be called load frame. And you would see that the quality of data depends a lot on the quality of the frame that you are using. Then the other important component is the crosshead. So you see this is the moving part. This one usually happens to be stationary, but this also acts like a crosshead. And this is also a crosshead. So crosshead is the one that moves up and down to pull the sample, and in which you would place your load cell. So before I come to load cell, let me write down crosshead. So this is another important component. Now you are pulling the sample, but you need some device which would actually measure what is the total load acting on it. And that device is nothing but a load cell. So usually you would have load cell attached to this, which would measure how much load is acting. And as a preliminary data, the amount of movement the crosshead makes, from there you estimate the elongation of the sample. So these are the three most important part or the units of the loading structure. So these are the three loading units. Apart from that, you will also have testing grips. So depending on whether you have a flat sample, a round sample, a threaded sample, you will have different types of testing grips over here. You will also have this load cell and or change in the elongation connected to a electronics, which will make the measurement and then give the data output to the computer. So you need a control unit and interface. So this interface would also be basically your data acquisition unit. Again, a good system would mean that it will acquire data at a much faster rate, and also transmit the data at a very high rate. Now, once the data goes into the computer, there you need an interface, a software interface, which will read the data and analyze the data. So you need a software. These are the most basic components of a UTM. Apart from that, nowadays you can also have UTM which do measurements at high temperature or under some humidity conditions. So you will also have temperature and humidity setup. And usually the setup would encompass or will contain the whole thing inside it, so that your sample is properly inside the at particular temperature or particular humidity condition. And in that setup or in that atmosphere, you will be able to do the measurements. So the overall system looks very simple, but you would be surprised at what is the cost of such units. Like I said, a lot of it depends. That good quality data depends on a good quality load frame, a good quality load cell. Then your grips should also be good quality, so that there is no micro slip. So you're holding the sample like this, and it is holding, the grip is holding like this. But if the grip is not holding properly, there may be micro slip, and because of that, the strain that you get would be erroneous. And no matter how good quality it is, there will always be some amount of micro slip. But then a good quality machine will try to minimize this. So a basic unit of such equipment would cost anywhere between 30 to 40 lakhs, a very basic unit, Indian rupees. And if you want some atmosphere or even very high strain rate, then the overall mechanics of the system, the load frame, they need to be much better quality. And in that case, you will have, so advanced units can cost easily as much as 3 to 4 crore Indian rupees. So you can see that this simple looking device or equipment is not so simple. It has a lot of cost involved with it, and therefore a lot of opportunity for innovation, so that one can make these systems at a much lower cost. In fact, there is an Indian company which has now already been bought up by a US conglomerate. So there is still a lot of opportunity of innovation in making a lower cost equipment like this. Okay, so now we have seen the overall setup, but one thing that is missing here is what is actuating or causing the movement of this crosshead. Now, overall, there are two different types of setups which can cause two different, you can say, origin of energy, which causes the actuation or actuation of the crossheads. And this can be classified into two categories. One is the electromechanical system, versus servo hydraulic. So in this one, you have basically a motor. So it may be a linear motor, which causes the movement, up and down movement of the sample, the crosshead, or it can be a screw driven system. So it's a motor which rotates the screw, and because of which the crosshead moves up and down. Or it can be a electromechanical system which pushes the piston up and down, electromagnetic system. On the other hand, in servo hydraulic, you have a hydraulic system which looks something like this. the shape, the overall functioning of this is what allows a very large amplification of forces here. So there is fluid in here, and there is a piston on one side which applies the force is in the other direction. So you apply the force in this direction. F1 area, cross-sectional area is A1. Here the cross-sectional area is A2. And this will cause the force F2. So you can clearly see F2 is equal to A2 by A1 times F1. So this kind of system allows easy amplification of the forces, and that is one thing. And here you have the liquid. Easy amplification of forces. So you can apply very, very large loads in this kind of system. Second is that since it is liquid, the movement is very easily or quickly transferred. So movement is very quickly transferred, or I would rather directly write the response is very high. But then this kind of system is also very expensive. On the other hand, electromechanical systems are much cheaper, but then their drawbacks are that response is not so high, not so quick. But the good thing is that it is relatively cheaper or less expensive. So these are the two different types of system which actuate the crosshead and cause the displacement of the or elongation of the samples, and which are then measured by the electronics, the displacement as well as the loads, and these are captured or recorded by the computer system. And then you can once you have the load versus displacement data, then from there you can obtain the engineering stress versus engineering strain, or true stress, true strain up to the UTS point. And beyond the UTS point, if you want the data, then like we said earlier, you will need to get the actual diameter of the neck region. And then you can also translate that data into true stress, true strain. So that is the one aspect of the machine. Another aspect that we need to understand about the machine is that what are the practical problems that may arise. The practical problems that can arise in a machine, and because of which so much science and engineering goes into making this machine, is that when you are applying the load, you should also realize that this load is also being applied back onto the equipment, and therefore the equipment will also deform. Okay, so first let me write, when load is applied machine parts also undergo deformation. So what type of deformation would it be? Would it be elastic deformation or plastic deformation? If it were a plastic deformation, then after every tensile test, the machine would have permanently changed a little bit, and then it would not be usable. So clearly it is not plastic deformation, it is only elastic deformation. Then the next question that may arise is that if it is elastic deformation, why are we concerned? We are concerned because the data that you are getting also involves or includes the elastic deformation of the system. Okay, so we'll see what we mean. So for example, let's say the crosshead is moving. So crosshead displacement will call, which is being recorded by the system. Let's call it delta LT. Now this delta LT recorded by the machine has contribution from various sources. One, it has the contribution from the elastic deformation of the system. It has the elastic plus plastic deformation of the sample, which is what you want to actually measure. This is the only part that you want to measure. And then apart from these, we also get what is called as micro slip. Like we said earlier, that you are holding the sample, but there will, because of the region where the grip is holding the sample, there will be some amount of slight amount of slipping, and that will also add to the total crosshead displacement data. So micro slip at the grip. Now this micro slip at the grip is something that we can minimize, but we cannot eliminate. For the time being, we will ignore that part. Let's look at what is the relation between delta LT and the delta LM, which is the displacement of the machine, plus delta LP, which is the displacement of the system. Now we know that force is equal to where is the stiffness. So if stiffness is the C times delta L. Now stiffness for the, what is the stiffness of the machine? Stiffness of the machine. This is related to the frame. It will be a function of the frame. How good is the frame? How stiff is the frame? Load cell, because load cell is also part of this frame. Then the clamping system, wherever you are joining two parts, their stiffness will also come into picture. So the machine, overall machine stiffness is actually function of several components, and these are just important ones. On the other hand, the stiffness of the sample is a function of the elastic properties. So basically the slope of the stress strain curve. Plus it is also a function of the cross-sectional area of the sample. And apart from this, whether how good the sample is made, the quality of the sample, for example, it may be flat or not so flat. So all those would go into determining the stiffness of the sample. Now, if we use this relation and put it over there, then we know that the overall stiffness of the system total is equal to the stiffness of the machine plus the stiffness of the sample. And this is a relation which is used to partition sample strain from total strain. And based on this relation, we also know that the crosshead velocity that we apply on during the elongation is not the same as the sample deformation rate. So the V deformation or the V crosshead is equal to Vm. So the rate at which the machine is deforming plus the rate at which the sample is deforming. So these two things together clearly tell us that the data that we obtain from the equipment has to be looked at carefully and understood properly. And if you do not carefully partition the data, you may get very erroneous data. For example, what you would observe is that strain without any external method of measurement. So if we are using only the crosshead for measuring the strain, so usually the system is called extensometer. So strain without extensometer are much higher. So that we can obtain from our relation over here. Delta LT is equal to delta LM plus delta LP. So this is the delta LT that you're calculating, but this is what you wanted. So this one is much higher than what you wanted. And if the strain is much higher, it means the stress versus strain slope in the elastic regime would be much lower. And therefore, modulus measured without extensometer are much lower. In fact, in one of the recent labs that we are doing in our campus, in the mechanical behavior lab, we measured the elastic modulus for aluminum samples, and it came out to close to 12 to 13 gigapascal, when the modulus of for the aluminum is close to 60 gigapascal, somewhere between 60 to 65. So you can see that elastic modulus becomes so much lower. Of course, this is very poor quality data. If we refine it, we can get much higher modulus, but still it will be lower than the actual value that you expect, which is close to 60 to 65 megapascal. So next is that now that we understand that strains calculated using directly from the crosshead is not accurate, so what is the better way? What are better ways to calculate strain? So whenever you are trying to get good quality data used for which you can use for publication, then you have to measure strain using one of these techniques. In fact, some of the papers and reviewers will not accept the data if where the strain has been calculated directly from extensometer. So one of the methods is extensometer. So extensometer is basically a device which sticks onto the surface of the sample. So let me draw roughly our sample. Okay, now what the purpose of extensometer is that it will have a knife type two edges, and then it ties up in one way or the other to the sample so that it remains stuck over here, and then this data will go into the electronics. Now when the sample is elongated, and this will become the gauge length for this. So now when the elongation takes place, it will measure only the elongation between changing the distance between these two blades. And therefore, this will give you a much more accurate, because it is not anyways being affected by the stiffness of the system or the micro slip. So everything gets excluded. So this system is able to exclude all that additional elongation data. The other method is what is called as strain gauge. So this is actually a resistance strip, a very, very small resistance strip. So you apply it over here onto the surface. So it has like this. And again, these are the two ends of the resistance wire. And what it is measuring is that when the length elongates, the resistance changes. So this system is actually measuring the change in the resistance, and therefore it needs to be calibrated a little bit. But once you have calibrated, this gives very accurate data. And both of these systems are able to exclude strain from the system, I will say elongation from the system, and microslip information data. And therefore, this method is very helpful in giving us very accurate data, and to be able to then measure even sensitive data like elastic modulus. So this lecture would have given you idea about the equipment, UTM, universal testing machine, or the tensile testing machine. And we have seen what are the important components, and we have seen what are the limitations and how to overcome some of those limitations. So with that, we will come to an end of this lecture. Thank you.